Hello, everyone, and welcome to this webcast. Now I think we are ready to start. My name is Søren, and I'm your host of this webcast today. So today we're going to hear an exciting topic presented by our two presenters, Andrea Obmann from Ford Werke and Jessica Rauch from Ford's Research and Innovation Center in Aachen. Jessica and Andrea are going to talk about ergonomic evaluation of handbrake in passenger vehicles. So the outline for today is that I'm going to give a brief introduction to anybody, and then you're going to hear the actual webcast. And after their presentation, we will have a question and answering session where it's possible for you to ask questions that may arise during the presentation. So, but first a little bit of introduction to anybody. It's a tool for musculoskeletal simulation, and what goes into this tool is the motion data, it's the kinematics, it's the forces. And what comes out is the body loads, the joint moments, the muscle forces, the joint reaction forces, so very detailed information on what goes on inside the human body. And this can be used for all sort of application. It can be used in sports, it can be used in orthopedics, universities. It can be used, as you will see here today, in automotive, aerospace, assistive devices, ergonomics, and consumer products. So really all sort of fields where, but what in common, of course, is that we do analysis on the human body and its surroundings. But with this, I want to hand over the presentation role now to our first presenter, which is Jessica, to give us a short moment to do that.
Thank you for the introduction. I hope you all can see my screen. In this presentation, we want to show you how we developed a process for the ergonomic evaluation of the handbrake. The project was a cooperation of 3 different Ford departments and the Institute of Biomechanics and Orthopedics from the German Sports University in Cologne. I am Jessica Rauch from Ford Research and will present the first half of this presentation. And my colleague Andrea Obmann works in Ford product development and will present the second part. She also did write her dissertation about this project. So when we talk about ergonomics and comfort, we first have to define what we mean, what we want to evaluate, and how we can do that. We know the perception of comfort and discomfort is very subjective. Especially comfort is something which is connected to design and features, and it's basically not predictable for us. It is also highly depending on factors like preferences and expectations, and it even can change over time. But we know that discomfort has negative effects on the comfort perception as well. And that's why we always try to achieve very low discomfort. And discomfort is associated more with physical factors like pain and fatigue and biomechanical factors. So this is more feasible to predict or to measure. And why is it even important for us to investigate comfort and discomfort? The simple answer is it is important for our customers and also becoming a differentiator on the market. So, of course, we try to maximize the comfort by developing new features and minimize the discomfort. Usually in the discomfort assessment for cars is done by studies with subjects, but these studies take quite some time. We need a lot of subjects and we need prototypes. So that's making these studies quite expensive. Objective factors are often really hard to measure, and a lot of stuff we can't measure at all. So we often rely on subjective ratings. But subjective ratings are often not really reproducible and consistent. So we need a lot of subjects and tries to get reliable information. That's the reason why we would like to have a virtual process using digital human models, which can help us to predict discomfort in early stages of the design process. And we focused on the handbrake. We are often asked why the manual handbrake. The electronic handbrake is coming into more and more cars. Does the manual handbrake even have a future? We think it has a future, and it is still important for small and low-cost cars, and especially in the emerging markets, we still see a future for the manual handbrake. And the handbrake is located in or near the center console. And this space is really loaded with a lot of different components, and there are more components coming. There are shifter, armrest, cup holder, storage for the smartphone, USB connectors, and other stuff. So you see there's quite some fight from all these components to get as much space as possible. That's why the handbrake location is becoming more critical, because they are, of course, trying to shift it out as much as possible. So that's the reason why we think it's important to evaluate handbrake position in early stages of the design process. And in previous research in the automotive sector, mainly focused on stuff like sitting or seat discomfort, joint angles, pedal operation, ingress, egress, and reach, but we could not find a lot about handbrake ergonomics, so we decided to do this study. Our objective was to develop a virtual procedure which can evaluate the discomfort of a handbrake design. Therefore, we needed, of course, to identify the factors which are influencing the perception of discomfort. And we had to look at how are people applying the handbrake, what motions they are using, and if we can simulate these. So we planned a multi-step study. In the first study, the preliminary study, we focused on the subjective ratings, and we looked to see if people can feel differences for different handbrake locations. And we wanted to see how people are applying the handbrake and if there are different motion strategies. In the second study, the main study, we again had subjects rating different handbrake designs, but at the same time, we recorded the motion and did a motion analysis. In the next step, there was a procedure developed to predict motions with RAMSIS. And this motion was given into the Anybody model, where we did get the biomechanical parameters, and these were used to develop a discomfort prediction model. I will give here a short overview about the pre-study and concentrate more on the main study later. The pre-study as well as the main study were completed at the Sports University in Cologne. And they invited more than 130 subjects, and we got complete data sets for 117 subjects at the end. The participants first made a test drive in a real vehicle, so we could find a valid seat position for everyone. This seat position was then transferred into a test rig with the same dimensions as the test vehicles. Then the subjects were asked to evaluate 8 handbrake designs, see 7 different locations, one was repeated, and their motion was recorded with video cameras. And of course, we measured several body dimensions. As a result from the study, we could see that the handbrake location does have an influence on the subjective discomfort. And we evaluated the videos and could identify different motion strategies, and we could also identify several people who were able to rate reproducible. And then in the main study, again, we invited 40 subjects, which also did take part in the pre-study. These subjects were selected so that they cover most of our driver population. And again, we did ask them to rate 8 handbrake locations in the same test rig. But this time we extended the range of the handbrake locations to cover most of the passenger vehicles. In the pre-study, we focused more on our preferred design space, but yeah, this time we did ask about, or we did extend the design space. We also modified the questionnaires and rating scales. In the first study, we had several questions, but we could see the simple question, how do you rate the application of the handbrake, was giving the biggest differences. This time, the motion was recorded with Vicon, and the handbrake was equipped with force and angle sensors. I will show you a short video here. I hope it will be transferred correctly and give you an impression about what we did. You see here, we had markers set up for everyone. We did a calibration motion. I explain later a bit more. Then we had EMG. You see this. We had questionnaires, and then here you can see how we changed the handbrake location and asked every subject to apply the handbrake at least 3 times. We recorded the motion and the forces, and they always had to subjectively rate each location. We also did maximum force measurements. With the results from the, I have to stop the video, it's running. From the marker, the motion analysis, we did go into anybody and tried to reproduce the motion in anybody, so we get the joint angles and the motion. First, we did go into, we do a calibration motion for every subject with our marker setup. We had a pre-scaled anybody model, which was scaled with the measured body dimensions. Then we had the marker set up, and with our calibration motion, we had more markers than in later when they were sitting in the car, because we also had markers on the back, for example. And so we could optimize the scaling and the marker setup. This is calibration motion. You could also see we had a belt with markers around the hip, because yeah, when seated, it's really hard to see markers on the skin. There's a lot of skin movement, and they often they are hidden, the markers. So we decided to use a belt which was really tight around the hip, and to get the real position of this, we also used this calibration motion, in which the subjects should move every joint at least once. And then with the marker setup, we had, from the calibration study and the scaling, we did go into the seated anybody model, where we had the measured handbrake forces and calculated the motion first of all. Yeah, we mainly concentrated then on the motion, because we could then see, I will change back to the presentation. We could see that the motion was quite linear between the start of the handbrake application and the end of the handbrake application. So we decided to concentrate on these keyframes because they were enough to define the motions. What we could also see is that the main things which were different for handbrake application was, of course, the torso and the right shoulder, elbow, and wrist joint. Not surprising. What we then could see is each subject had to apply the handbrake 3 times. So we had for every subject 3 data points. And we could see there was already quite some variation in each of these trials. And also, of course, between subjects, there was quite some variation. But what we could see is influence of the body height. Okay, maybe the black points are from the start keyframe for the elbow location, for one handbrake, elbow flexion for one handbrake location. And the red points are the end elbow flexion for the same handbrake location. So what we could see, the difference between this, so the motion was always quite similar for every subject. Applying the handbrake for a certain angle always means they are doing a certain elbow flexion. But what we also could see, it was depending on the body height, the start position and the end position. For small females were more flexed than for tall males, for example. The variation for every subject was quite big. And so we decided we are concentrating on our key percentiles, which we also want to use for our virtual process, which are always used with thought with digital human models. So we tried to find the values, the regression values for small females, tall males, and 50 percentile females and males. And with this data, we tried to develop the new processes, which will Andrea explain a bit more.
Yeah, thank you very much, Jessica, for this very nice presentation. I will now shift the presenter role to Andrea.
Good morning, everyone, and thanks a lot, Sören and Jessica. I hope that you can see my screen now. So additionally to the motion, we also analyzed the discomfort ratings. And what was very important to see is that there was no significant difference for the location, which was assessed twice. So this confirms a good reproducibility. But what we could see is that there was a difference in the rating for different handbrake locations. So yes, the handbrake influences the discomfort, or the handbrake location influences the discomfort perception. What we can conclude from the box plot here is that the variance of the ratings is depending on the handbrake location. So, for example, for the center handbrake locations 1 and 8, for example, there is a small variance in the discomfort ratings. However, for the lower locations 4 and 5, we see a larger variance of the ratings. One contributor to this is the influence of the body height on the discomfort perception. Here on this slide, we can see that the discomfort perception depends on the handbrake location, and that it's different for each handbrake location the correlation between discomfort and body height is different for each handbrake location. So For handbrake location 4, which is the rear low handbrake location, smaller subjects perceive more discomfort than taller subjects. This is easy to explain. So smaller people typically sit more forward in the vehicle to be able to reach the pedals and more upward to see sufficiently. And when then the handbrake is in a rear low location, they have to apply it in a very uncomfortable body posture. We call it chicken wing posture. And for taller people, they typically sit more rearward and lower in the vehicle. They can apply the handbrake in a more comfortable body posture. For handbrake location 5, the four-low handbrake location, it's the other way around. There, taller people perceive more discomfort. They have to lean forward. For handbrake location 8, one of the center handbrake locations, we do not see a correlation between body height and discomfort. Let's focus now on handbrake location 4, the rear down handbrake location. The variance of ratings, it's large, even for subjects of a similar body height. And so it does not make sense to predict with our process the ratings of single subjects, and we decided, similar to the body angles, to take the regression line values as targets for the discomfort prediction. Though again, we use the main percentiles, 5th percentile female, 50th percentile female, 50th percentile male, and 95th percentile male. And here, for example, we see the target discomfort value for the 5th percentile female at handbrake location 4. The next step was modeling the motion. We used RAMSIS. RAMSIS is a digital 3D model, and it has anthropometric and posture models. So there are many anthropometric databases for several countries and regions in the world, and it also offers a wide range of posture models. For example, car driver posture model or truck driver standing posture model, and those posture models are based on empirical studies. RAMSIS is used by almost all automotive OEMs. For driving related application, typically the car driver posture model is used, and it worked well for predicting the driving posture, the steering wheel adjustment and the seat adjustment, but for predicting the handbrake postures, it didn't work well. So we got unrealistic postures, and it seems that the empirical study this model is based on does not sufficiently account for handbrake application. So it was obvious that we would need to develop our own posture models, or new posture models. Philip Reiber did this in his master thesis. First, he tried to predict the postures with one posture prediction model. This didn't work well. So he developed a posture prediction model for each key percentile. And the good thing is that the 4 models can all be applied with the same set of constraints and can be used for start and end of handbrake application prediction. With this, we got posture prediction, which was well in line with the postures derived from the study, as you can see here in the pictures. The next step was the biomechanical modeling. And you probably all know anybody as you dialed in this WebEx, so I will only say a little bit about it. So it's a rigid body model, and you can choose from a lot of different models and details. And when you do a study, you first have to define all those details. On the next slide, we see that, for example, the body model, muscle model, scaling models, and muscle recruitment model have to be chosen. And I will not go through every detail on the slide. I will focus on the muscle model. So as muscle model, we have chosen the any muscle model. In this muscle model, the strength of the muscle does not depend on the actual length and contraction velocity of the muscle. Why have we chosen this model? One reason is that handbrake application happens at pretty low speed and the model length is not extreme. Another reason was that we did some comparison of this model and the 3E muscle model, which is more complex. It simulates the hill muscle model so that the strength is dependent on actual length and contraction. But in previous studies, we found that for some postures, the any muscle model was more robust and the 3E muscle model overestimated the strength of the muscle or the muscle path changed during the motion. So we used the any muscle model as it was more robust in previous studies. After choosing the models and settings, we used the postures and the time constraints and the handbrake force to do the kinematic analysis and then the inverse dynamic analysis. And with that, you can calculate a lot of different biomechanical parameters in any body. And we concentrated on, or we focused on selected biomechanical parameters for our analysis. Joint angles, muscle activities, joint reactions, joint moment measures, and we also analyzed the metabolic power and energy consumption values. So here we see what the simulation looks like. The blue lines are external forces and muscles which are applied are shown thicker. Now let's go to the next slide. After that, we did the correlation analysis. We correlated the factors and also their squared values to the target discomfort. And we use squared values as, for example, for the body angles. It is to expect that squared values will correlate well. For example, a spine rotation in the one or the other direction might increase discomfort, or for other body angles, there might be an ideal value for which the discomfort will be low, and for increased and decreased body angles, the discomfort will increase. We did the correlation analysis for 3 time steps. The start time step is when you start to apply the handbrake and your hand is at the handle, but there is no force transfer between the hand and the handle. The second time step is based on the same posture, but this time with force transfer between the hand and the handle. And the third time step at the end of the handbrake application, when you apply the handbrake so that the vehicle holds on a slight hill. We did the analysis, of course, for all handbrake locations and the key percentiles. And what was very good is that in all factors groups like body angles and joint moments, we found moderate to good correlations, which were highly significant. And I think this is very good because discomfort is so subjective, and this is the first indicator that discomfort of handbrake application can be predicted using biomechanical parameters. I will show one example for correlation. So here we see the discomfort versus the right wrist abduction moment at the end time step, and wrist abduction is bending the hand towards the thumb. And we see that with an increasing abduction moment, the discomfort increases to high values for discomfort, and the abduction moment are, for example, for the 5th percentile female and handbrake location 2, which is the rear up handbrake location. For developing a discomfort prediction model, we use stepwise regression, and with each step, we increase the prediction quality and decrease the standard error. And with 9 predictors, we found, or we had a very good quality of prediction, or we had a very good prediction quality. So we could predict 96% of the variation, or we could explain 96% of the variation in discomfort. And the standard error was 3.5, which is very good when you compare it to the absolute difference of the location, which was assessed twice. It was 3.9. And unfortunately, we do not have time to discuss every predictor in detail, so I will summarize. The first 89% of the discomfort can be explained by the first five predictors that are predictors all from the end time step, joint reaction, joint moment measures, and also joint angles. And the last four predictors become especially important for combinations of handbrake location and key percentile, which lead to unfavorable start postures. They are all from the first two time steps, the start and the first time step. On this slide, we see an overlay of the ratings, which are shown not filled, and the predictions, which are shown with gray filled symbols. And we see that for all handbrake locations, the predictions are well in line with the values we derived from the study. And one thing which is also very good and very interesting to see is that the mean rating from the 40 subjects can be predicted with the 4 percentiles based on the regression values or based on the prediction. And that is very good to know that we can predict the group discomfort with the mean of the 4 key percentiles. So with this, we can say that we now have a procedure we can use for prediction of the handbrake application postures and the discomfort. So the geometry of the vehicle and the handbrake are used in RAMSIS to predict the postures for the 4 key percentiles. With these postures, in any body, the biomechanical parameters are calculated, and with this, we can then calculate the discomfort for the 4 key percentiles and compare different handbrake variants. So to summarize on that, so the prediction quality is very good. It's comparable or even better than most similar studies in literature. So as Jessica mentioned, we didn't found much on handbrake discomfort. So most similar studies were based on reach or application of other control elements. And yes, we were successful in developing a procedure to predict handbrake application postures and to predict discomfort. And we meet both requirements we specified at the beginning, that it's reliable and user-friendly, and that it's based on digital human models which are available at automotive manufacturers. Yes, the model is ready to be applied. And what we can conclude from the limitations of the study is suggesting then potential future research topics. So it would be interesting to see to what extent the results of this study can be transferred to other populations, other handbrake design, or other control elements. It would also be interesting to find out if additional parameters could increase the prediction quality or reduce the number of predictors for discomfort. Additional parameters could be the shape of the handle, the influence of armrest design, the interface pressure between the human and its environment. And with this, I would to thank you for your attention and give over back to Sören now.
Yeah, thank you, Jessica, for this very nice presentation. I will now take back the presentation role. Yeah, so just a little bit more information before we move on to the question and answering session. So previous webcasts are available on our YouTube channel, and There's also on our website, there's also a possibility to see a publication list where you can find information on all sort of topics that our user have been using our software for. There is also a upcoming events page where it's possible to see that on December 4th we have the next webcast, which is a novel workflow using the antibody modeling system and mechanical finder to do finite element analysis on osteoarthritic gait. On March 4th in 2019, there is a musculoskeletal modeling workshop at the Laboratory for Biomechanics in the Ostbayerische Technische Hochschule in Regensburg in Germany. So if you're interested in some of these upcoming events, then go to our website and sign up. And you can find more information on all these things.